All right, so remember, typically when I give you a warm-up, I don't give you more instructions that are on the page, because if you're not sure what to do, I want you to work through that and try to figure out what to do. It's a skill. It's called problem solving, right? Even if I show you a million problems, you're always going to find another problem that's a little different. So if you have the skill to kind of think it through, figure out what it's asking, come up with an answer, that's a skill that will serve you, right? So, for instance, the fourth one, write the equation in factored form. We really haven't touched on that a ton with polynomials. So I want you to think about where you've seen the word factored form before, right? What does factored form mean, right? How can I take what I've gotten in the first few questions and turn it into a factored form, right? Now, I highlighted this part. You don't actually need to divide. It says use the graph of this to answer the following question. So that graph has something to do with this, right? It says, what is the remainder when the function is divided by -3? But I just told you you don't have to divide. How could you find the remainder without dividing? So you got to think about that. What did we talk about last class? What does the remainder represent? Hold the thought, because I still want people to try to work on it, right? So think about what the remainder actually is in terms of a graph, okay? And that should help you answer those questions, and then give number 4 a shot, okay? And I'll give you a few more minutes to work on it. So, for your warm-up, again, I'm telling you that you don't actually need to do the synthetic division. I mean, you could to check your work maybe, but let's say we were going to do it. Well, I would be dividing this, and then this is the thing it wants me to divide by, right? That's the root it would want me to divide by. So I would set up this thing, right? -3, put my coefficients in, 1, 5, 2, and -8. And then I'd have this little spot for my remainder. But that's the thing. I don't actually have to do this. The question is asking you to predict what that number would be without even doing the synthetic division, right? And that's where yesterday's lesson came in, right? Because and it says use the graph, so that's kind of a hint that the graph has something to do with it. So, go ahead, Leo. What can I do here? How do I not do this but still get my remainder?
So it's asking you to divide by a number. That number is your x value. You go to that x value and find the y value on the graph.
Exactly, right? So if I go to where x is -3, which is right here, right? And I find the point there for the graph, it's -3, 4, right? So I know that if I did do synthetic division, if I did go through all of that, I would do all the math, and I would get a 4 there, right? That is what we learned yesterday, is that synthetic division actually gives you points. The x is what you divide by, the y is what you get as your remainder, right? So I can answer this question. What would the remainder be when we divide by -3? It would be 4, right? I didn't even do it. I just know by looking at the graph. What would the remainder be when you divide by -1? -6, because that's right here. -1, -6, right? And then it says what divisors, meaning plural, would give you a remainder of 0. Well, yeah.
-4, 1, and -8.
-8? Back over here?
Oh, no, on the y.
Oh, no.
No?
So that's when, this point down here is when x is 0.
Oh, and
Your remainder is your y value, right? So -4, -2, and 1. Now, there's 2 ways we could have known that. We could have thought back to when we first learned about synthetic division, and the whole point was to find roots, to find x-intercepts, right? And when we found a remainder of 0, we're like, yay, we have an x-intercept. We found a root, right? So that was one thing. But then we learned why that worked. Why does that work? Well, if I did all this work and I get a remainder of 0, that's still the remainder theorem. It's still the output to that input. Because think about what every one of these points is. This is -4, 0. This is negative 2, 0. This is 1, 0, right? The remainder is 0 because that's the output. That's the output that goes with the input, right? So I know that if I divided by negative 4, negative 2, and 1, I would get a remainder of 0 because that's the point on the graph. Those are my x-intercepts. Those are my roots, right? All right, now this last piece, it says write the equation in factored form. So you got to remember what factored form is, right? And we're going to use that word factor a lot today. We're going to talk about it and make sure we know exactly what we're talking about when we say factor, okay? So where have we seen factored form before? Intercept form, right? So for instance, this is not this graph, just as an example of factored form. You might have had like y equals x plus 5, x minus 3, right? That's factored form. That's a quadratic. That would be a parabola, right? And it's called factored form. Why? Because these are the factors. I'm going to be a little annoying. Why are they the factors? What makes them factors? What is a factor?
X-intercepts.
They're the x-intercepts, but why do we use the word factor? Yeah. Divides cleanly, and then you could take them and you could do what? You could rebuild the original, right? Think about the word factor, and when you first saw it in your math journey, right? If I asked you for the factors of 6, or some factors of 6, there are multiple, what factors of 6 would you give me? 2 and 3. Why are they the factors? Why are those the factors of 6, or some factors of 6? Because they multiply to give me 6, right? 2 times 3 is 6, therefore those are factors of 6, right? So think about that. Like, when we say factor, let's not just use the word. Let's think about what it means. I'm taking a bigger thing, and I'm breaking it down into the multiplication of littler things, right? I'm taking the bigger thing, and I'm breaking it down into the multiplication of littler things. So for instance, this, well, maybe I got this, and the problem started out with x squared plus 2x minus 15, and I factored it, and I got that, right? I had a bigger thing, and I broke it down into the multiplication of littler things, right? That's factoring, right? That's why we call it factored form. That's why we do it, because this doesn't tell me as much as this. This tells me the x-intercepts, right? So the other thing is, if I know this, I know my what? My x-intercepts, which we also call solutions and roots, right? But I also, if I know how to use this form, and I know my roots first, then I know my form, right? Because if I started out by saying, hey, your roots for this parabola that I just made up are negative 5 and 3, and then I said write it in factored intercept form, right? You would say, oh, that's x plus 5, x minus 3, right? Roots to factors, factors to roots. Okay, that was quadratics. Let's come back to this problem. If I know my 3 roots, right? These are my roots. Can I write this in factored form? Right? Somebody give me the first factor that I could write. It doesn't have to be in any order, but give me one. Go ahead.
Oh, yeah. Will it be x plus 4?
X plus 4, right? Somebody else give me another one. Go ahead. X plus 2. Somebody else give me another one. X minus 1. Now, we're ignoring one little piece for now. What are we ignoring? Anybody know? No, we've covered the roots. What can functions do sometimes? Stretch, right? So I would have to actually tell you, and I should have put it in the problem. A is 1 here, okay? Figuring out A is like the final boss of the unit. Like, that'll be harder, right? So we'll just say that a is 1, and that way you can just imagine a 1 out there. But if I tell you a is 1 and I give you the roots, you can write in factored form by just switching these all to factors. Now let's make sure we get what my main point is about this word factor. Besides the fact that we know roots turn into factors, what makes these factors of the equation that we started with? And talk about the word factor and what it means. What makes this the factored form? What makes these the factors of that original equation, besides the fact that we know we can turn roots into factors? Yeah?
Because if you multiply them together with one of the given roots or solutions that you have, then you get, well, y equals 0 is what you want.
Okay, so you're talking about solving, which is good. Yes, if I set 0 for f of x, and then I would get roots, and I would get my solutions. That's what makes them factors that can give me my x-intercept. Sure, but just think simpler. What makes them factors like 2 and 3 are factors of 6? Why are these factors of that? Why are 2 and 3 factors of 6?
Similar.
Yeah.
Because they're multiplying, but those are factors of that because if you multiply those, you'll get that.
Exactly. So we gotta hammer this home. These are factors of the first equation that we started with, right? This equation. Because if I took the time to multiply this all out, I would get that, right? Remember what I said a factor is. It's to factor, meaning the verb, is to take a bigger thing and break it into the multiplication of smaller things. Here's the bigger thing. Here's the multiplication of smaller things, right? This is multiplying, right? It's more complicated than 6 and 2 and 3, but it's the same concept. If I can go back and forth, factoring, multiplying, I have factors, okay? So when I ask you to factor, that's what I'm asking you to do, right? It's a word that has meaning, so it's important to understand its meaning. All right. And we'll talk more about it, obviously, when we get to the rest of the notes. Back to the lesson. Go ahead. All right. So lesson. Okay, so let's go back to that word factor. Let's hammer this home. Okay, so factor as a verb. A verb is something that you do what with?
You actually do it.
Yeah, it's an action, right? So if I tell you to factor as an action, I'm asking you to do the factoring, right? So that's the one I'm talking about right now, right? The verb, which is to do. When we factor, this is what we're doing. Ready? We break down a polynomial into, I'll just put parentheses, right? That would / could multiply to give you the original equation, right? So that's just a fancy way of saying big thing to smaller pieces. That are being multiplied. Right? Just like 6 became 3 and 2. Okay? Now, the noun factor, right? Just because this was a question in another class, right? That is one of the pieces. Right? So it's one of, if you say, hey, what is a factor? Is this a factor? It's just one of the pieces that you broke the thing into, okay? Now, to factor is not the same as to solve, right? And that's an area that we get confused about. In fact, on your last quiz, a lot of people, I asked you to factor, and you went all the way to solving, right? Sometimes you got to factor in order to solve, but solving is another step altogether. Solving means to find a solution that makes something true. Factoring is just breaking it down, right? So I would just write not the same as solving, right? When I'm solving, I'm setting y equal to 0. I'm doing zero product property. I'm trying to figure out what x is equal to, right? Here, I'm just breaking it down, okay? Now, there's a couple ways to factor that we have exposure with, but we're going to use them now for polynomials, for things that are bigger than quadratics. So if you have any room over to the side, I'm going to show you, I think that showing you an old example will help. So let's say I said factor, and then I gave you, let's go, 2x squared plus 20x plus 48. Okay? And I said factor it. Now remember, factor, this is the big thing. I'm trying to get you to break it down into smaller things. So what would I do? Anything we notice right away? 2 goes into everything, right? We call that GCF. So I'm going to pull out the GCF first. So I pull a 2 out. It doesn't go away. It just comes out front. Divide by 2, divide by 2, divide by 2. And I would get x squared plus 10x plus 24. Okay, so have I factored this? Yeah, this is a bigger thing that broke down into multiplication of smaller things. Not that much smaller, but it's still kind of smaller. Now, can I factor it more? Because you always want to ask that question. Can I keep factoring? Yeah, because this actually is magic xable, right? 24 and 10, right? So that would give me 2, oh, sorry, I didn't finish it, 6 and 4. 2 times x plus 6 times x plus 4. And now it's fully factored, right? So sometimes there are multiple steps. First you factor one thing, then you notice you can factor something else, right? But think about what a factor is, or what factoring is. We had this bigger thing, and now it's the multiplication of smaller things. That, and that, okay? So we're going to continue with that concept, okay? But we are going to have to get comfortable with a certain type of GCF, okay? So for instance, remember when I gave you like x squared minus 5x, and I said factor it? A lot of you were just like, I know he told us a new way, but I'm pretty comfortable with magic x, so I'm just going to pretend c is 0, and put 0 on top, minus 5 on the bottom, do my magic x, and I said, you don't have to do all that. There's a GCF here. What's the GCF? X, right? X goes into both of these, right? We don't like to sometimes think about variables as GCFs. We think numbers, but if anything can be divided all the way across evenly, it's a GCF. So this would become x times x minus 5, right? Because you could go back. If you can go back, then you factored correctly, right? X, if you distributed this, you'd get x squared minus 5x, right? So this is factoring. Bigger thing, multiplication of two little things, right? So there's your intro. What do you think I could do to factor this? This cubic function. Yeah, everything, x goes into everything. So here's a very important thing. Just because you're dividing doesn't make it go away. It just goes out front, right? You're undistributing it, right? So if I divide all these by x, well, on the inside I get x to the third divided by x is x squared minus 4x divided by x minus 4x and minus 5. And then I ask myself, can I keep going? I always ask myself that. And then what I notice is the inside kind of looks like a magic x again. So I go magic x, minus 5, minus 4, minus 5, positive 1. And this thing, which I broke down into two things multiplying, now I will break down into three things multiplying. X minus 5, x plus 1, right? Now I look, again, that can't be factored, that can't be factored, that can be factored, I'm done, right? Fully factored. And it's three little things that are being multiplied to give me the bigger thing. Okay? Now, sometimes we do have a number, and sometimes we have a letter too. So you might get something that looks like this. All right? When you get numbers and letters, you look at them both one at a time. And you might want to just on the side say, let me figure out my GCF here because this is kind of complicated. Numbers first. What goes into both 3 and 48? 3, right? And what goes into both y to the 5th and y to the 3rd? Not just y. You want the greatest common factor. Sure, y goes into both of them, but y to the 3rd also goes into them, and that's greater. So 3y to the 3rd is my GCF. So now I pull out 3y to the 3rd, and I divide them both by 3y to the 3rd. Well, in this case, the 3's cancel. Y to the 5th over y to the 3rd. It's y squared minus, and then 14 divided by 3, 16. And then y to the 3rd over y to the 3rd cancels. Okay, now I ask myself that question. Can I keep going? Who says yes?
Yeah. It's minus 4 plus 4.
Very good. What do you call that, Hannah? What is another word for subtraction? Starts with a D.
Dividing.
No, not dividing. If I said, yes, difference. It's the difference of, what are both y squared and 16?
Number?
Perfect squares. Perfect. Yep. So the difference of perfect squares. The reason I'm hammering home that name is because it has everything right in it. You need everything in it. You need the difference, so that's subtraction, and you need perfect squares, right? If you're missing either of those things, you can't keep going. But we have them. So we go 3y to the 3rd, more broken down little pieces, right? And then you square root both, so you do y and y, 4 and 4, minus and plus. And now you're fully factored, okay? Difference of perfect squares. It's going to come up a lot, actually. So make sure you're getting practice with that. All right, so that's one type of factoring. There is one other type of factoring, and then we'll be done, okay? And this one should look a little familiar, too, right? We've done something like this before, okay? And I know I have some ones for you to practice with. That was if we had time, but we kind of spent longer than I thought. Okay, so this is called grouping. And this is what you can do when you have 4 terms and no GCF. Okay? If you have a GCF, you would want to pull a GCF first before you do this. Okay? Now, when you have 4 terms, it's like rainbow, it's grouping. Another time, it would be good to remember the name because it's right in the name what you're going to do. If it's called grouping, what do you think we're going to create? Groups. And this will be my first group, and this will be my second group. Remember this? And then we're going to GCF each group. Okay? So what goes into this group, both of these things? X squared. And if I divide them both by x squared? X to the 3rd divided by x squared is x, right? X squared divided by x squared is 1. And then over here, what goes into both? 7. And then this divided by 7, this divided by 7 is? Okay. Now this next step confuses people, so I'm going to take you to the side. If you have x squared, and let's say you were times b, and then plus 7 times b, and I told you to GCF that. What could you GCF out of that? B. You would say b, and then you would divide this by b, and divide this by b, and you'd get x squared plus 7. Now, what if I told you that instead of b, it's x minus 1? Right? All I did was put a placeholder in for this. You can't cancel it. It's a GCF. X minus 1 is your GCF. It goes into both. You could divide them both by it, right? So you say divided by x minus 1, divided by x minus 1.
Which means you would do x.
You don't have to actually show this step every time.
But x minus 1 and then parentheses 2 squared
X squared.
x squared plus 7.
There you go. That's why grouping works. Okay? Now, the other way to remember this, if that was super confusing, because I know it can be, is if you get the same parentheses twice, bring that out front, and take the other two pieces and throw that out back. Okay? That's the step, right? But I want you to understand the concept. We are just GCFing one more time. Okay? All right, so can I keep going?
Yes.
No. Remember the name. Difference of perfect squares. We got two problems. Is that a difference?
No.
Is that a perfect square? No. So I'm done. Okay? All right. And you're done. But if anybody wants grouping steps, I'll write them on the board, okay? If you want to write down some steps for grouping, okay? And then also, you got a few minutes. There's some practice ones for both situations, so maybe pick the one that's more confusing. Dive in, right? And practice a little bit while I hand out your homework, okay? Here are your steps. You're going to split them into groups. You're going to factor GCF in each, and then GCF one more time. And then, in other words, the parentheses goes in front. Everything else in the back. All right, let me get your homework. But let's go to the homework, see if there are any questions. Okay, so to the homework. Okay, so on your homework, remember, the new skill was, hey, we can use synthetic division to find outputs when we have inputs. When I have an x, I can find a y by finding the remainder, right? So to get you started on the homework, I just did a couple traditional synthetic division for the sake of dividing. Like, I'm not asking you about inputs and outputs. Remember what we use synthetic division for in the first place, to divide and find a answer. Like an answer to the division, right? So, would anybody like to see either of these? To just see that classic synthetic division example. Okay? Okay. Now, I won't go through this problem. Can somebody give me the answer, though? For number 2. So this, remember, this divided by that, right? You can think of it as a fraction where you put it underneath, or you could see it written that way. What is that divided by that? Can somebody give me what they got? 2n cubed.
Minus 2n squared minus 2n minus 5.
So minus 2n squared minus 2n minus 5? Does that look right?
Yep.
Okay. Now I'm going to ask you a question based on this conversation we just had. What are the factors, or at least some factored form of that? How could I write that in a little bit of a factored form? Yeah.
If you take the n plus 6,
Multiply it by the answer that we just got.
Yep. So because I know that this divided by this is this, just like I know 6 divided by 2 is 3, therefore 2 times 3 is 6, right? This divided by this is this, so this times this is this, right? So it's important to understand this because we're going to need all of this knowledge going forward, okay? So when you divide, you are getting factors, right? Maybe I can continue to factor this further. Maybe I can't, but I've started to factor. I had a bigger thing, and now I can represent it by 2 smaller things, somewhat. Right? And then we're going to talk about today, like, You can keep going, maybe, and then make it even more smaller things, right? That's factoring, okay? All right, moving on. The next it was like, all right, let's use the new skill now. Let's find the remainder in order to find an output, in order to find an y when I have an x, a point on the graph, right? The remainder will tell us the y with any given x, right? So there were 4 of these. Does anybody have one of these in particular they would want to see? 6? All right. Actually, 5 is like the hard one. So wait, so which one, say again? You said 6? Okay. And you said 4? Okay. And 5. All right, so we are going to divide by this. What did they give me, the root of the factor? This is a potential root, right? Now, a factor would look like this, right? Why is it important to know this? Because when we do synthetic division, we divide by the root, not the factor. So what number should go on the outside? 5, right? So 5, and then coefficients. This goes from 4 to 3 to 2 to 1 to nothing. Perfect. I don't have to add anything in as a placeholder. So 3 minus 16 plus 8 minus 9 minus 30. And then I always put that box there. No matter what, I put that there right away, just so I don't accidentally think that's part of my equation. I know it's my remainder at the end, right? Okay, so bring down the 3, multiply, add, multiply, add, multiply, add, multiply, and I get 0. Okay, so there's a couple things we figured out here, but what was the question that was asked? It wanted you to give an ordered pair, which is a what and a what?
X and a y.
It's a coordinate point, right? It's an x and a y. Well, they gave us our x. I know it says a, right? But sometimes we see different letters. And we found our y. So our answer is 5, 0, right? When the input is 5, the output is 0. When the x is 5, the y is 0, okay?
Is it going to be 5 or -5?
Well, it's 5 because we go with the root for our point, not the factor. If you think about it, if you ever forget, just think if I had a minus 5 in an equation, where would the x-intercept go? At 5, yeah. Okay, so this is our input, this is our output, this is our x, this is our y, right? That's what we figured out. We also kind of answered another question, but I'm not even going to write that equation because that's not what they asked for, right? I could if I wanted to, but that's not what they asked for, okay? All right, number 4, still need to figure that out, or does it make more sense now?
Yeah, it's good.
Okay, number 5, I just want to at least set up because it's a little bit of a tricky one because it's missing something. What is it missing?
N squared.
N squared. So you always got to check, do I go 3, 2, nope, I'm missing my 2. So it's as if I put in an imaginary plus 0 n squared there. Just a placeholder, right? And now I have 1, 0, minus 7, minus 1, and I do the synthetic division, I'll get my remainder, right? I can do that, it doesn't take very long. 1, 3, 3, 9, 2, 6, 5. And you don't have to do it that fast. But the reason I can do it that fast is the same reason I think you should use this instead of the old way of finding your outputs. Because I didn't do any complicated math there. 3 times 1, 0 plus 3, 3 times 3, 9 minus 7, 2 times, I mean, these are elementary school math problems, right? And I don't say that to say you can't make a mistake. Of course you can make a mistake. You can make a mistake anywhere. But you always want to set yourself up in a position where you're least likely to make mistakes, right? And calculators just seem to be a spot where we can make mistakes. So sure, you could plug 3 into that equation, but now you have to do parentheses 3 to the cube minus 7 parentheses 3 minus 1. Maybe make a mistake in there, especially if there's a negative somewhere, right? This thing kind of avoids that stuff, okay? So my point would be 3, 5. Okay? Make sense? Now, the last piece of your homework that you needed to do is just graph a full equation, right? So you can't forget where we come from, where we know that something to the fourth that's not reflected is going to look something like this, right? We know that from our knowledge of n behavior, what a fourth function looks like, a degree 4 function looks like. There's no negative out front, right? It might be good to just draw that little picture on the side so we know we end up looking like that at the end. But now the expectation is we're actually going to have some points and make this thing a good graph. Now, this thing gives you some advice in the directions. It actually tells you what numbers to put in. -2, it says, hey, do some synthetic division for -2, -1, 1, and 2. What did it skip? Why? Why shouldn't you do synthetic division for 0? Don't you want the output when... Right, so it is because you should already know that, right? Or at least you could already know that. Because my C value is always my value at 0. And why? Well, think about the old way. If I plugged in 0, 0 to the fourth, well, it's 0. -3, 0 squared, that's 0. All I have left is -3. So anytime you plug in a 0, you get the last number, right? Now, the synthetic division you would do for the other ones, right? And I'll do one of them, and then we'll fill it in. So -2. Okay, now take a look at this function. If it starts at 4, right, as a degree, it needs to go 4, 3, 2, 1, 0 in terms of its exponents, right? What's missing?
3 and...
Yeah, so a couple, right? And this can happen. 0x to the third needs to go in here. And then also, I need a 0x to the 1 in there, right? So that's a couple placeholders, so just be careful. So I end up with 1, 0, -3, 0, -3. And then I'm looking for that remainder. Bring down the 1, -2, -2, 4. This is one spot where I do see mistakes. Negative times a negative is a positive. Just be careful with your sign. 1, -2, -2, 4, 1. Okay, so what did I just figure out?
-2 equals 1. It's -2 1.
Yeah, the point is -2, 1. Yeah. Well, if -2 equals 1, then I've been wrong this whole time I've been teaching. But no, I know what you meant. Okay, so -2, 1, right? So we found a point. We just do that a bunch of times. You see it didn't take very long, right? And then we fill in the table. And it would be -1, -5, 1, -5, and then 2, 1. And we add those points to the graph, right? -2, 1, -1, -5, 0, -3, 1, -5, 2, 1. Now we said it should end up looking like a W, right? Does anybody see the W shape there? Right? Yeah, so that's why it helps to kind of make a little sketch, because now I can go through these points and feel good about it, right? There's my W, right? So, all good. Now, the last piece of this homework asked you about n behavior. Remember, I'll do that real quick. As this goes to -infinity, where does y go? Positive infinity, right? So you would say as x goes to -infinity, y goes to positive infinity. And then as it goes to positive infinity, y again goes to positive infinity. So as x goes to positive infinity, y goes to positive infinity, right? In notation, I would practice the notation because you will need to do that, so you might as well get good at it. Yeah. So yeah, okay, so that's the homework. All right,